So resolution refutations are useful for checking whether a set of things is a contradiction. And one way it can be used is by figuring out whether an argument somebody made is valid or not. Moreover, you don't even need to know the intermediate steps. You could just look at all the premises, look at the conclusion, and check whether this conclusion indeed follows from those premises by a valid argument. So how would we do it? So remember, an argument is valid if the formula that says end of premises implies conclusion is a tautology. And if something is a tautology, that means that its negation is a contradiction. If you reverse the truth value of every single cell in the final row of the truth table, if they were all true, now you get all false. So to check that something is a tautology, it's enough to check that its negation is a contradiction. And the formula end of premises imply conclusion is very nice in that respect, because if you negate it, you end up with end of premises and not conclusion. So as long as all of your premises are CNFs, and you can make your negated, definitely negated conclusion a CNF, you ended up in something in this nice CNF form, which you can verify whether it's false or not, whether it's a contradiction or not, by using the resolution refutation, by using the methods that people use in automated provers. So here's how you could check whether a certain statement can follow from certain list of premises by a valid argument. You take the statement and you negate it. You convert the negation of that statement and all the premises to CNF form. And finally, you write a formula, premise 1 and premise 2 and so on, and not conclusion. If you can get a resolution refutation of this formula, if you could derive false, then your original argument, which was the negation of the thing, was valid. If you figured out that this thing is always true, the original thing false, the original thing must have been always true. So let's try to do an example. And let's go back to our treasure hunt. So remember, we had the following premises. If the house is next to a lake, then the treasure is not in the kitchen, and so on and so forth. We introduced variables for all the propositional statements. This house is next to the lake, yes, no. And then, by doing natural deduction magic, we decided that the treasure is under the flagpole. Let's check if what we did was actually solid. Let's check that our argument was valid. And here we are not going to look at the intermediate steps. We are just going to check whether the conclusion, this particular conclusion, indeed can follow from the premises by a valid argument. By the way, that means that it's not that we are checking that the argument we did was valid. We just check whether it's possible to create a valid argument with this conclusion. So what are we going to check is that end of our premises implies our conclusion is a tautology. Here was our argument, and we ignoring the part 6 and 7. So let's look at the argument again. There it is. So this thing will be a tautology if the argument is valid, which means that the same thing with, rather than imply D and not D at the end, will be a contradiction if and only if the argument is valid. Remember, when we negate F implies G, we get F and not G. When we negate end of premises implies conclusion, we get end of premises and not conclusion. That's exactly what we are getting here. So let's try to check whether this argument is valid. Let's go and convert all the premises into CNF form a negated conclusion into CNF form. Well, there is not much to do with the conclusion because it's just one variable. So negated variable is perfectly good CNF formula. And so this is the formula that we end up with. So this is the formula that will be a contradiction if the argument is valid. And now we have this formula in the CNF. Finally, we could use resolution refutation of that final formula in order to check whether indeed those premises, those Q's, imply that the treasure must be under the flagpole. So let's do it. First of all, we need to find two clauses that have opposite literals. So the first thing we could do a resolution on, well, we actually have a lot of choices here. We could do it on not A or not B together with A, which is kind of what we did when we were doing natural deduction proof, but let's just for a change do something else. From the first two clauses, one has not B, the second one has B. So the leftover part of the first one is not A, leftover part of the second one is not C. Here we get not A or not C. Good. Let's say now we do go and use that clause that just contains A, and now together with what we just derived, we can get not C. Separately, we could use the negation of our conclusion together with the clause C or D. By the way, here C, D stand for the trees in front is elm and treasure is under the flagpole. They are not variable like we had before, which mean the whole clauses. They just mean one thing. So C or D, not D, will give us C. And finally, we derive not C, we derive C, we can derive false. So again, this may be a bit confusing because now we are using A, B, C, D, E, F to mean variables, and right on the previous slides we use the same letters to mean formulas, but really it's just a matter of using different letters, and we try to stick here with the letters that we use for the natural deduction proof. Okay. So it's very common when we are doing logic and we are doing natural deduction to give puzzles that are murder mysteries. Well, I don't like murders. So let's take something that's a murder mystery and make it just a tiny bit, maybe less scary. Here is a puzzle. Imagine a cat fight. The family of mother cat, a father cat, and a son and daughter kittens. Very much a murder mystery, not quite murder. Nobody got killed, but one of those cats attacked and bit another. One of the cats watched, another one hissed at the fighters. Here are some things that we know. Here are the 4 clues. Now you need to figure out which nasty cat was the attacker. Try doing it with natural deduction. And most importantly, trying to solve the puzzle and then track the steps of your thinking to see what rules you were using at every step. Were you using modus ponens? Were you using resolution? Were you writing things as a CNF formula, or were you just writing every clue as whatever logic formula it was? And moreover, think, did you end up use any knowledge which is not listed here? So one of the big things in automated proving is that you need to explicitly tell all the facts to the system. For example, you know that if you have 3 people and the first one is younger than the second and second is younger than the third, then the first one is younger than the last one. Well, the system might not know it explicitly. You may need to explicitly tell us, oh, by the way, this is a rule about being younger. Also, maybe you need to tell the system that the mother cat must be older than her son and daughter. So try to solve this puzzle, and as you're solving it, think, how would you program a system to solve it? Think like a computer scientist.